This is lesson 19 for AP Calculus. We're talking about volume of revolution. This is different than when we've talked about volume where we sliced through an object and got these slices that were like circles or semicircles or triangles or squares. This is where we have basically, it's not a floor, but we have this object that's two-dimensional. It's got an area. It's not three-dimensional. It's a flat, planar thing. And we pick one of the axes, and we can see it by this diagram right here where it's got this thing, circular little motion marker. And what I'm saying is we're going to grab the y-axis, and we're going to spin this piece of paper as fast as we possibly can. And as we spin it really, really fast, and we look at it, we're going to all of a sudden kind of see a three-dimensional object. It's kind of like those flip books where you flip the corner and all of a sudden it looks like animation. That's what's happening here, is you're spinning this around so fast that you see a three-dimensional object. And when you spin this triangle, this right triangle, around the y-axis really, really fast and keep spinning and spinning and spinning and spinning, so it's revolution, it's rotating, you end up with a three-dimensional object that looks like a cone. And our job is to find the volume of this three-dimensional object, this cone, that is created by spinning this two-dimensional object around the y-axis. If we have this semicircle right here, this two-dimensional, just on a xy plane, there's not a z plane here, this is just an xy plane, and I grab the x-axis, and so you can see this little rotation mark here. I'm going to grab the x-axis, and I'm going to spin this as fast as I possibly can. Spin, 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 spin. The shape that you would start seeing is this three-dimensional object that is a sphere. And again, we're going to talk about how we would find the volume of this. Well, in both this sphere and in the previous slide, this cone, if we were to slice perpendicular to the axes that we rotated, so here we rotated on the y-axis, so I would take slices perpendicular to the y-axis, or in the second one, where we would have this sphere, and since we rotated on the x-axis, I'm going to take slices that are perpendicular through the x-axis. In both of those three-dimensional shapes, these slices would be circles. So then this becomes very much like the problem that we had, the problems where we had a floor plan and then we sliced and had certain shapes that we sliced. These will always be circles. So how do we find it? It really isn't much different in the fact that we're going to be talking about circular areas, but what is the floor plan? It's not a floor plan. It was a two-dimensional object that we spun, and in fact, it would have been half of the floor plan when we think of this as volume by slicing. So let's look at this problem here where we have a function square root of x. We also have a boundary at y equals 0. Now remember, y equals 0 is the x-axis. And then we also have a boundary at x equals 4. Our first job is to sketch these boundaries and see what that looks like. So here is what it looks like, this sketch that we've got the square root function. We've got the y equals 0, which is the x-axis. We've got x, and then we have x equals 4. So we have this vertical line right here. And then I shade in that region, that bounded region. It says to rotate it about the x-axis. So again, in my sketch, you make a little wheel right here. You say, there's my little wheel. This is the axis I'm going to spin. So we're going to spin, spin, spin this, and we're going to create some three-dimensional object where we're going to have circles that are perpendicular to the x-axis. Well, this distance from the function to the axis of rotation is the radius of the circle. This is what the object would look like. We see we have these discs, and that's why we call this volumes by discs. We always end up with these slices that are discs. it's perpendicular to the x-axis, so that's going to be dx for finding our volume. And we have circles, and the radius of the circle, this r right here, is from the x-axis to that function. So how do we find that volume? Well, it's pi r squared is the circle, and so it's just like we did before. We take the integral from our 0 to our 4 of the circle and dx, because so we have the area of the circles, and then the width of each of those discs is dx, and we would have the volume. I'm going to leave that for you to do because this will be a problem you're going to have to do, but you could do this by hand and find the volume of this three-dimensional object. Let's look at example 3. We've got boundary, same thing. We've got f of x equals the square root of x. We've got y equals 2 this time. And we have x equals 0. So y equals 2 is a horizontal line. X equals 0 is the y-axis. Step number 1 is to sketch this object right here, this two-dimensional object, this bounded region that I'm going to shade in. And so here it is. It's this, we saw that square root function, but because we're coming to the x-axis, actually the y-axis with y equals 2, and we're using the y-axis, this becomes the bounded region, this right here. And it says we're going to rotate it about the y-axis. So once I know that, I'm going to do a perpendicular right to the y-axis, and that's going to be where my discs are, and that is the radius of the circles. We also want to draw a three-dimensional sketch of what that would be, and we have it here. So it's this kind of funnel-looking thing. It's actually be a beautiful piece, made out of clay or something. It's pretty nice looking. But we're going to have all these circles. And since these are dy's, because we're perpendicular to the y-axis, we need our equation in terms of y. Right now it's in terms of x. So we have to take a moment and rewrite our function. I'm going to be doing these discs. And our function, we say, is square root of x. So I have y equals the square root of x. I square both sides to get what x equals, and x equals y squared. So this is the function that we're going to be using. And we're still going to use pi r squared because it's a circle. The r is that radius right here, and that radius is y squared, because it's going to be y squared, the right function minus the left, y squared minus 0. So it's always that function to the axis of rotation. Once again, you can figure that one out. So these are the formulas for you to memorize and to, you're going to be using them in your homework, but you really need to memorize them. When you're rotating about any horizontal axis, any horizontal. We've been doing it around the x-axis, but it could be some other horizontal axes. We're always going to have the volume is equal to pi, the integral from a to b of whatever that radius is. Now, this radius, since we've been doing it to the x-axis, it's just the function. But if my horizontal axis was something like y equals 2, I would have to subtract the top function minus the bottom function to find the radius of the circles. Okay. And when they're vertical, we're rotating around the y-axis, we have the same function. It's just that our r has to be in terms of y. Okay. You have some problems. You have two handouts. This is one of the first handout. This was really meant to be like classwork and to get this done before the end of the period. And then you have the other handout to do as homework.